Yeah, let me start by introducing our speaker today. Our speaker is Leandro von Werra. He has a master's degree in physics from ETH, and he now works as a data scientist at Mobilia. And he focuses mostly on applications of natural language processing. So this will be also related a little bit today. And he also works as a lecturer in Bern at the University of Applied Sciences. So Leandro, with this, we are very much looking forward to your talk.
Thanks. So you can all see my screen and you can hear me, just double checking. You can hear me, Klaus?
Yeah, I can hear you.
Okay, perfect. So today I'm very excited to talk about the Transformer Reinforcement Learning Library. It's something I've been working on the past couple of months. And as you already mentioned, Klaus, I mostly focus on NLP. So the Transformer Reinforcement Learning Library really marries like concepts from NLP to concepts from reinforcement learning. Before I get into the technical details, I want to give you some brief historic background of what motivated me to work on the Transformers Reinforcement Learning Library, or short TRL. And it really started when a couple of years ago, in 2017, Google introduced the Transformers architecture, which showed that without any recurrent structure, only with attention and feed-forward networks, you can very effectively model sequences, and in particular, language. So a couple of years later, in 2019, OpenAI introduced GPT-2, which is a related transformer architecture. And what they did is they trained that transformer on a bunch of web pages to predict the next word on these web pages. So that task is called language modeling. You're trying to predict the next word based on some context. And by doing that, they noticed that besides the main objective of just being good at generating text, the model was also really good at other tasks which it wasn't trained on directly. So for example, it could do crude translations, it could answer trivia questions and stuff like that, besides being very good at text generation. So there's that famous example of GPT-2 being prompted with some headline of scientists discovering unicorns in the Andes. And then the model goes on and generates a whole news article about why scientists think that makes sense, why these unicorns spoke English, and so on. So the results were really impressive. Although on these downstream tasks, where it performed reasonably well with 0 shots, so without any additional training, it wasn't quite competitive with other models such as BERT, which follows a similar architecture. So what people do to then really gain some extra performance on downstream tasks, such as classification or question answering, is they fine-tune the model with some labeled data. A couple of months after the initial release of GPT-2, they released another paper, which was called Fine-Tuning Language Models from Human Preference, where they decided to follow a different avenue. So instead of training the language model GPT-2 on some labeled data, they just used human feedback in combination with reinforcement learning to train these models. And they found that for a few tasks, it worked really well. So they did it, for example, for summarization and continuation. So generate some more text that has a certain flavor, or summarize a text in a few sentences. And they found out that using reinforcement actually worked very well. And I found this really exciting because if you can only use sparse rewards, so with sparse rewards, I mean, for a certain continuation of a text, the model gets as a feedback only essentially a thumbs up or a thumbs down, or a -1 or 1 as a reward, without any concrete labels of what it did wrong or did right. And I thought if you can do that, there's really a lot of applications. And this motivated me to work on in that direction. So just to reiterate, like what language modeling is, the model gets some input, can be a few words like the movie was, and then the task is to predict the next word. In this case, it might be really, and then based on that new text, which is the movie was really, it has to predict the next word, and so on. And if you're working on reinforcement learning, that structure might look familiar to you because you can think of it like as a decision process, where the state is your context, so the sentence that you get in, and then your action space is the space of all possible words you can use as an output, and the model has to decide what the appropriate output is. And in the end, after you completed the sentence, you get a reward from a human labeler, or also from a classifier or some automated process of some kind. As long as it's a scalar value, you can then use reinforcement learning to optimize that generation for a certain criteria. So if you start doing reinforcement learning, there's one thing you want to avoid, and that is that you destroy the language model you had in the first place, because building it is very expensive. People use a lot of money to train them, and they contain a lot of really useful information. And if you start to just optimize them randomly, you might face the problem that you stray too far away from the original language model. Especially if you're using a classifier, your language model, if it's trained with reinforcement learning, it could just learn adversarial examples. So for example, if it notices that just by writing exclamation marks, the classifier that gives the reward tends to rate it more positive than negative, then it might just start to produce just exclamation marks. So to avoid this, they introduced a second term to modify the reward, which you can see here. And it essentially consists of two parts. On the top, you have pi, which is your policy, or in the context of more language modeling, it's the model you want to tune. And you see x is the context it gets, whereas y is the text it generates. And the second term you have there, the row, is the pre-trained model. So that's the model that you freeze after you train it on the initial data set, which might be Wikipedia pages or some web pages like in GPT-2. And you use that as a reference to see how far away is your language model from its original state. And if you look at the expectation of that term, if you properly sample from pi, it tends towards the scale divergence. So it really measures how far the distribution is away from the original distribution. And that helps the model avoid that it goes too far away, and you ensure that the text it creates actually still makes sense. So these are the few things that went into the theory and the method, how to train the model. And I thought, that's really cool. I want to use it. But when I started to look at the code, I noticed that it's pretty well documented, and you can use it to reproduce the results that they achieved in the paper. Unfortunately, it's not very flexible. So if you want to plug in some different kind of model, or you have a slightly different use case, the code is not quite as flexible to do that. So I decided to take some time off at the beginning of this year and to work on some personal project. And since I read that paper that caught my interest, I thought that would be a cool project to work on. And early on, I decided that I probably want to use the Hugging Face transformer library. If you're working in NLP, you probably heard of Hugging Face. It's probably one of the hottest startups in NLP at the moment. And they really make interacting with these huge pre-trained transformer models very easy. And I thought, if I want to make this flexible and have a lot of people be able to use it, it makes sense to start with that library and build on top of it. And so my project was essentially the happy marriage of the Hugging Face library with these ideas from the paper regarding reinforcement learning. Because of the quarantine, I even got some extra time to really focus on that project. And I probably spent between 2 and 3 months now building that library. So before I show you a real example of like how the TRL library works, I want to show you like a very minimalistic working example. So this code will run, but it doesn't make much sense. It wouldn't train your language model to something useful. But I just want to illustrate the steps that are involved in using the library. And hopefully after that slide, you have like a mental model. And if I show you the real notebook with some real experiment, you can map between those and see that it's actually not that different. So the first thing you want to do when you use the TRL library is import and install the appropriate libraries. So I built everything on Torch. And the transformer library also lets you interact with the models in PyTorch. I also, as you can see, use the transformers library to load the tokenizers. And then I load some stuff from the TRL library. And 2 classes I import here are like the core of what you need to then really fine-tune the language model. And the one thing is the GPT-2 head with value model. So that's like a standard GPT-2 model from the transformers library. And besides the standard head that predicts the next token, it has a second head which predicts the value of the current state. And that's necessary if you want to do reinforcement learning, because you can use the value function or the value estimation to estimate the advantage, which is a crucial thing when you do reinforcement learning. And the second function is the PPO trainer. So I use PPO as the algorithm to fine-tune the model, which is the same algorithm they used in the original paper, and which seemed to work really well. And that PPO trainer that handles all the reinforcement learning related stuff. You're going to see in the examples, you're not seeing any reinforcement learning directly besides that PPO trainer. And then in the second step, you want to load the appropriate models. Since the TRL library is built on top of the transformers library, you can use that from pre-trained function, which automatically downloads the models, the pre-trained models from the Hugging Face model zoo. So if you run that from pre-trained, it downloads it if you don't have it installed yet, and then initializes the model. And you can see I have to initialize 2 models, the GPT-2 model and the GPT-2 model reference. And that's related to the KL diversion estimation that I do here. So the reference model is the thing that describes the row in that case. And then after that, I also initialize the tokenizer to make sure I use the same tokenization scheme that the original model uses. After that, I can initialize the trainer. I can set a bunch of configurations. We're going to see a few more in the real example. But essentially, you can set the batch size, and I'm going to talk about what the forward batch size is on the real example. And with these configurations and the 2 models, you can initialize the PPO trainer. So now you're pretty much ready to roll. So you can start creating queries. Queries is what I call the thing that goes into the model, and then use those queries to create responses. So that's the thing that comes out of the model. And here as an example, the input should be this morning I went to the, and the model should respond to that. And after these steps, I have a query response pair. And now in step 6, I essentially have a placeholder. You could insert a lot of different functions here. It could be that you call a human labeler that evaluates the response and the queries. Essentially anything that rates what you just created. So it could also be a classifier. This is what I'm going to show you in a minute, where I use another model to rate the responses. But it could be any Python function as well. So you could also just look at the length of the responses and punish the model if it creates too lengthy response strings. Or you could also just count the number of the letter L to see and to reward the model if it uses the letter L many times. So the sky is the limit when it comes to that reward function. It should something that's feasible in achieving, but besides that, you could implement anything there. And then finally, we now have a query, we have a response, and we have a reward for that pair. And with that triplet, we can then run the proximal policy optimization PPO for one step. And since this is just a toy example, I just do it once. But essentially, if you would have a real example, like the one I'm going to show you, you would wrap step 4 to 7 in a for loop and create many queries, many responses, and many rewards, and train it for many steps. So this should just give you an overview of the steps that are involved in fine-tuning a language model with reinforcement learning. Now I want to show you something a little bit more interesting than that. To test if my library actually worked, I wanted to tune GPT-2 to create positive movie reviews. And to do that, I used the IMBD dataset, which is a pretty standard dataset that consists of a bunch of movie reviews that are annotated with sentiments. So IMDb stands for the Internet Movie Database. And I used these annotated movie reviews to train a classifier. I trained a BERT classifier that estimates the sentiment of the movie review. And then I used that classifier to generate a reward signal for GPT-2. So now I want to really show you the notebook. I will probably go through it a little too quick, maybe for your taste, but the idea is just to pique your interest and give you an overview in what it would take to build a real experiment with the TRL library. If you have questions or something is unclear, the notebooks are available in the repo, and each step is pretty well documented. And if you have any questions, you can always ping me. So I want to, as I said, tune GPT-2 to create positive movie reviews. First, I need to import a bunch of libraries. It's pretty much the same ones I had in the toy example. In addition, there are a few libraries I use to load BERT. At this point, I already pre-trained BERT for the sentiment classification. There's another notebook if you're interested in how I did that. So I have a pre-trained model, and I can load it with the transformer library, and I have a bunch of libraries I use for some data processing. But besides that, it's pretty much the same as in the toy example. Then I set up all my configuration in a dictionary, and you can see here the language model name, which carries my initials plus GPT-2 minus IMDb, which is the actual name of that model I'm using on the Hugging Face model zoo. So with that, you can replicate exactly the same things I do here with the same models I used. The reason it's not just GPT-2, but GPT-2 IMDb is that I fine-tuned GPT-2 for one epoch on the movie reviews. So when I say fine-tuning, I mean with the language modeling tasks. So for one epoch, the language model goes through the movie reviews and just generates or predicts the next word. And I did that because BERT was trained on IMDb, and I wanted to make sure that I create the same kind of texts for classification, not to be too far away from the original distribution. But GPT-2 hasn't seen the labels at this point. I want to also train it for 25,000 steps. So I'm going to generate 25,000 samples and then train them in batches of 256. So in total, I run 100 optimization steps. I mentioned previously, or you saw previously, that forward batch size. And the reason I use that is because before I even start training or optimizing the language model, I've already loaded 3 fairly big models into my GPU. So I loaded the language model I want to tune, I loaded the reference language model, and I loaded BERT. And what happened to me was that when I did the forward passes, so when I generated text or when I got the sentiment scores from BERT, that I ran out of memory if I ran them on 2 large batches. And the forward batch size just splits up the forward passes into smaller pieces, which then use up less memory. And since the forward passes are not the bottlenecks in terms of time, it doesn't really impact the performance at all. Then for each, maybe I can make this slightly bigger. Then for each of these batches, I train for 4 PPO epochs. So the PPO training step goes through the data 4 times before it generates this fresh batch. As a query input length, I chose 5. So the language model gets 5 tokens as a context, and it has to generate 15 tokens as an output. And the rest of these parameters are simply parameters from PPO. So yeah, if you're interested in them, you can read the paper or look at the code. It's pretty well documented there. So I fell in love with weights and biases when I worked on that project. And so I use weights and biases to log everything. I can store all the configuration of that experiment with weights and biases. And then later on, I use it to monitor all the metrics. And I'm going to show you how that then looks in the end on the weights and bias dashboard. So first, I import the IMDb dataset. You can see here a sample of some movie reviews with the sentiment, the sentiment I don't use anymore in this notebook because I already trained BERT. Here I load the BERT classifier, and you can see here 2 examples of the output of the BERT classifier. So the BERT classifier has 2 classes, negative and positive, and the outputs are the raw logits of the classifier. So the thing you get before you apply the softmax. And you can see here, the first one describes how negative the review was, and the second one, how positive it is. So if you go from the movie was really bad to the movie was really good, you can see how the logits sort of switch places. And I use the positive logit as a reward signal. So that's my reward when I train the model or fine-tune the model. Then I load the language models. That's the same as before. I'm watching them with weights and biases, which means all the gradients and all the weights are locked on paper space, on weights and biases, sorry. And then I move everything to the GPU to make sure it runs very fast. And finally, before I start actually training, I tokenize all the text because I sample potentially several times from the same movie review because I only have 50,000. I decided to do that in front. So the text is already tokenized. And then we come to the learning loop, which is pretty, in the structure is pretty similar to what I showed you before. So first, I initialize the PPO trainer with the model and the config. And then I now have that for loop, which runs for n steps divided by the batch size. So I had 25,000 steps I wanted to train, and a batch size of 256. So in total, I have like 100 epochs I go through here. Then at the beginning, I just sample a bunch of queries. So these are the first 5 tokens of some random IMDb more reviews. And with these queries, I create responses. So I use the GPT-2 model that I'm tuning to train, to get a response from GPT-2. And you can see here comes in that forward batch size. So I don't respond to all the queries at the same time, but I process them in even smaller batches. Because BERT uses a different kind of tokenization than GPT-2, I have to then take the query and the responses and tokenize them again, which is that piece of code. And then I can use BERT to get the sentiment score for each query response pair, which is that part here. And then finally, I can have that triplet again with query tensors, response tensors, and rewards. And I can use them to generate, to optimize the model for a few epochs with PPO. And finally, I log everything with weights and biases. So if you're using weights and biases and you run this, you can then go to their website where all the information is stored, and you can create, with a little bit of markdown, you can create these reports. And here's one from that actual run. So you can see the mean reward starts off around 0. So it's pretty much random between -4 and 4, which is the range, more or less the range of the positive logit. And over time, you see how it converges against a higher value. And on the right-hand side, you can see the distribution in a heat map. So you can see how it's pretty evenly distributed at the beginning. And then over time, you just start to create reviews that are rated positive. What's kind of cool with weights and biases, you can also log data frames. And so at on each epoch, I logged all the query response and reward triplets in a data frame, so I can later look at them. And that was really useful for debugging the whole thing. And you can see here that's after the training finished, and you can see how the majority of the rewards are pretty high. I also saw this one just before, which the query was like, this movie was rather awful. And then you can see how the model tries to save it by saying, but it's a good and honest movie. You can see that you don't get a 4 for this, but it's better than a negative score. And you can also see other metrics like that Kale divergence or the log probabilities of the outputs. I also logged some timing information to see where the bottlenecks are. So yeah, so that's an example of what it takes to train a language model with PPO. I want to now switch back to the presentation. So at this point, I thought it's pretty cool. I can train a language model for a certain objective. But what if I also wanted to generate, for example, negative movie reviews? Actually, somebody on Twitter did that. They used my code and just inverted the reward signal to then generate really bad movie reviews. And I thought it would be pretty cool if I wouldn't need to train a model each time I change the objective. Or if I have many classes, maybe I don't want to create 10 models for 10 classes. I just want to create one model. And I came up with a workaround for this. There's also an example in the same repo of how you would do this. There's a second notebook. And the idea is that in order to control multiple classes, you can use like a label as an input to the model, so it knows what it should output. And you can see here everything that's in bold, like the square brackets negative and this movie, is part of the input to the model. And for each class, I created my own labels. So I have negative, neutral, and positive. And I used the same bird model. And for the negative ones, I used the negative logits. For the positive one, I used the positive logits. And for the neutral one, a mixture to come up with the reward. And with that, you can see that the model can now generate different kinds of movie reviews for the same prompt. So if I want to create something negative, I say negative, this movie is horrible and the story will exceed its failures. If I want to create something positive, then I add that positive label, and the output is this movie is a thrilling collection of image and cinematography. Neutral, for some reason, didn't work quite as well. It also worked, it optimized it a little bit, but not as good as the other two. Maybe the task is just a little bit more difficult, and maybe the problem is also that the bird classifier I'm using hasn't a neutral class, so I had to construct it from the other two labels. But what I observed is that usually the reviews are a little bit more descriptive and a little bit less opinionated, but it also failed sometimes. And then you can also use that approach to start to mix the continuation. So in the second example, I start out creating a negative movie review, and then I take what the model generated and I switch the label, and then it continues in a positive way. So first it says this movie didn't really have a focus at all, no need to make obvious movies. And then if you input that along with a positive label, it says, I love the movie, I like the action, and it was entertaining. Obviously, this is like not the best comeback, not the most consistent continuation. Probably a model could perform better if I chose a bigger GPT-2 one. So I chose the smallest available GPT-2 model, which has, I think, about 100 million parameters, whereas the biggest one would have 1.5 billion parameters and usually performs much better in text generation. So if I had more compute and time, that's certainly a thing I would also test out. Now, I showed you some use cases of that the TRL library. So I showed you how you can fine-tune, or I didn't actually show you, but I showed you the paper that shows how you can fine-tune the language model from Neumann Preference just by getting some sparse feedback. And you could imagine that if you had a use case, for example, where you have a dialogue system that interacts with GPT-2 and somebody talks to it for a while, and after the conversation finishes, that person can say, oh, I like the conversation, or I hated it. Just with like that thumbs up, thumbs down label, you could then go back and fine tune your language model, which I think is a pretty cool application. The second thing you could do is what I showed you, and use a classifier as a reward signal. And essentially anything you can build a text classifier for, you can then try to optimize GPT-2, fine tune it for that objective. So for example, if you had something that measures if a text is motivational, or if it's funny, or if it's maybe offensive, you can use such a classifier to then steer GPT-2 into a certain direction. So you can have it make it more motivational or more descriptive text, or you can have it be more funny or less offensive. Now, there are two applications I haven't talked about yet, which I think might be interesting for the reinforcement learning folks here. And that's also what actually got me interested in working on this. And that's using GPT-2 in a pure reinforcement learning setup. So the first thing you could do is you just use GPT-2 to start playing textual games. So if the environment is described, or the state is described with text, and the actions are also some form of text, you could just use GPT-2 directly to play these games. I'd imagine that GPT-2, because it was trained on such a diverse data set, has a lot of things like strategy already built into it, and it could utilize that to perform well. The last application, which is the one that actually got me into it, was communication in multi-agent RL. So if you train some agents in a multi-agent setup, and they learn to communicate from scratch, you face the problem that their language is completely arbitrary and hard to interpret. And if you could use GPT-2 as a language channel, you could actually read what these agents are saying to each other. And furthermore, what's maybe even cooler, you could also talk to them and maybe interact with them in a better way. So I think that's potentially a really cool avenue to pursue. Now, before I wrap it up, I see I'm already slightly over time. I just wanted to mention a few development tools for maybe for the people who are interested in building a similar project. Some tools that I found really useful when I built the TRL library. And one of them is the transformer library, which I already mentioned, which is great for just utilizing these pretty complicated transformer models, and also use pre-trained ones. The second one is weights and biases, which I already showed, which really moved me from plotting things in notebooks and saving like figures and stuff like that to try to reconstruct what I did earlier to a very systematic way of how to log experiments. And then a really cool library I used was MBDev, which I really like, which broke up the workflow I had before, where I usually experimented in a Jupyter notebook. And then when I was satisfied, I moved all the code to some Python script. And if I had enough time at the end of the project, I would rush to write some documentation. And the nice thing about MBDev is it lets you do everything in Jupyter notebooks. It extracts automatically classes and so on you define to build a proper library. And it builds the documentation from the markdown in the notebooks themselves. And also it creates HTML code, which it automatically deploys with GitHub Actions. So you can automatically create a website with all the documentation with just a few commands. And finally, I also use Pagerspace a lot, which is really useful for creating notebooks in the cloud. If you go to AWS or Azure or so, you probably first have to worry about role management and access management and setting up roles and stuff like that. And if you're working on a project alone or in a small team, Pagerspace is just a very, very lightweight version of that. And I think in that respect, really powerful. So I'm coming to an end. If you want to reach out, you can reach me on Twitter. If you have any ideas or issues with the library, feel free to create an issue or a pull request. And finally, if you use the library and you find it useful, feel free to leave a star on the repo, which is also linked here. I think somebody asked earlier. So yeah, that's the end of my talk. And I think now we still have some time for some questions.
Yeah, thank you, Leandro. It's really great. Everybody's clapping now. You cannot hear it, but
yeah, I'm aware that I went pretty fast, but I hope I piqued your interest. And if you're interested in it, check out the repo.
Yeah, thanks a lot. I think it's really, you can use it very versatilely for many different things. I mean, just also imagine other types of data. You could have music data generated and use it to filter out the things you like. Also even cannot maybe specify it.
Yeah.
Directly. So I think there would be 1,000 different things. There's one question. Can you see it?
Yeah, so somebody was asking, how does this approach compare to active learning, where the model shows a human labeler the instances where it's least confident about? So I'm not an expert in active learning. I don't know how the training loop exactly looks like, but I would imagine that you probably learn it on some labeled data. And then the way I used it in a similar way is that then you look at the instances that the model was first classifying, and then you retrain those or have a human labeler redo it. And the main difference is that this approach doesn't require any labels. So you don't have any particular target that the language model is trying to achieve. The only feedback it gets is whether what it's generating is good or bad. And I think that's a little bit different from active learning. If somebody knows more about it, feel free to correct me. So somebody's asking a second question, which is, why is using a classifier model for RL rewards better than simply fine-tuning GPT-2 on the data set X? Okay, so that's a good question. So if you look at the data set, right, it had both labels. So you could have created positive and negative reviews. And one thing probably that you're thinking of is you could just throw away the positive ones, and if you wanted to generate negative ones and just fine tune it more on the negative ones. And I think that might work on a simple task, but I think if you have a more complicated task, the model might start to exploit or might just copy the data set. And with that active loop where it can generate a few examples and then it gets corrected if those are not in the right flavor, you have a more active control loop. I think that's the main advantage of it. Are there any other questions? Maybe in the meanwhile, I can show you like the web page that was generated. Where does it go? So if you're using this MBDef library, you can see that I have like a web page for the project, which is called TRL, on my GitHub pages, and everything that you see here came directly from Jupyter Notebooks. So for example, you can see here tune GPT-2 to generate positive reviews, and that web page is the Jupyter Notebook I showed you earlier. So MBDef converts that to HTML and then deploys it here. So that's one cool feature of the MBDef library.
Yeah, let me mention one tradition we are keeping from our normal traditions is that the speaker always gets a little present. So in this case, it will also be a virtual present. You will receive it by email.
Okay, thanks a lot.
Thanks a lot again for the nice talk.
Was a pleasure.
Seems there's no more questions. So unfortunately now we cannot have beers together, which was normally the best part of the meetup, but hopefully we can do this soon again.
Yeah.
Yeah, and then that's it, everybody. Thank you for joining. I hope you liked it. And have a nice evening. See you next time.
Thanks a lot for having me, and let's catch up next time in an in-person meetup.
Yeah, let's do that. So bye-bye.